Whenever we're dealing with three-dimensional space, we have this sort of convention of how we normally label our axes. So this is the conventional way to do it. So I remember this by thinking, well, you have to remember that the z-axis is up, right? So the positive z-axis is facing up, and then of course the negative z-axis would be down here. And then if you were like looking from above, like a bird's eye view, the xy plane should be how it's normally oriented, with the positive x on the right and the positive y being like up. There is another way to do this. Another way to do this would be like this. Where I make the z-axis positive on the bottom and negative on the top. And you can tell that this is a different orientation because, and you have to have a good imagination for this, but imagine your index finger is the x-axis and your hold on, if your index finger is the x-axis, your middle finger is the y-axis, then your thumb should be the z-axis. And whenever I say that, I mean the positive, right? So your index finger is the positive x-axis, your middle finger is the positive y-axis. That would make your thumb the positive z-axis. You can tell that no matter how you rotate your hand, you can never get to the red orientation on the right. Right, so as long as your index finger is the positive x-axis and your middle finger is the positive y-axis, then you can't make it so that your thumb is the negative z-axis. It just, you can't make it so that you match that orientation on the right. There's actually only two possible orientations for these axes in three-dimensional space. So like if you make up something else, like let's try this. Let's call this y, x, and we'll call this z. Again, this is actually the same as the green orientation. This orientation in green on the left is the same as this purple orientation. Even though I changed the axis labels, right, you can just rotate your hand and you can get to this purple orientation. So every single way that you could label these three axes, it can either be rotated to match this green orientation or it could be rotated to match the red orientation. So whenever I talk about the conventional orientation, I'm talking about this one. So this is the one that we're going to be using. This is the one that your textbook uses. If you see this, because sometimes I think already this semester I've labeled these axes like this, notice that it's actually the same under a rotation. You just have to rotate that 90 degrees and then you get the same orientation. But we're always going to avoid doing this. We're going to avoid sort of the right hand orientation, and we're going to try to keep the left hand orientation as much as possible.
What kind of orientation would that be? Like three composed rotations or just one rotation?
You mean to get the one on the right?
Yeah, like the one.
You'd have to make a reflection. There's no composition of rotations that would make it work. Yeah.
Like rotating this way and then that way and the other way.
Well, so if you started from the green orientation, right? You started from X, Y, Z like this. There's no possible way to rotate your hand to get to the red orientation. That's what I mean by those are different. The green and the red are fundamentally different, so that you cannot rotate them to match the other. The green and the purple are actually the same. The green and the purple are just a little rotation away from each other. But like the purple and red are not the same. You can't go from purple to red, for example. Yeah. And so that's why we try to avoid doing this one in red. We try to keep the orientation that's in green. Okay. So the next thing is cylindrical coordinates. And to remind you, back in Calculus 2, we had rectangular, or we also called them Cartesian after Descartes. Cartesian coordinates where you had x comma y. We learned in Calculus 2 how to go back and forth between this and polar coordinates, where you had an r and a theta. So when we talk about 3D space, our new rectangular coordinates are going to be the coordinates x, y, and z, like we've been talking about so far. But we're going to learn how to go back and forth between that and these cylindrical coordinates. And in cylindrical coordinates, we're going to have the coordinates r, theta, z. And these cylindrical coordinates, r and theta, those mean the same thing as r and theta meant back when we were talking about polar coordinates. The z means the same thing as the z does in rectangular coordinates. So I'll try to draw this as best I can. My z-axis goes like this. Now in cylindrical coordinates, the r is going to be the distance from the z-axis, and the theta is going to be the angle, between that point and the positive x-axis. Okay, so here is my y-axis, here is my x-axis. So here's a point over here in space, and if I imagine the projection of this point onto the xy plane, there's going to be some angle theta between that point and the x-axis, and then there's going to be some r, which is, we're talking about the distance from that point to the z-axis. Does that make sense? And so you'll notice for anything in 3 dimensions, any coordinate system you can come up with still requires you to provide 3 numbers to fully describe where that point is in space. Now you can describe it with the x, y, and z coordinates, or, like we just have seen, you could describe this with the distance from the z-axis, the angle from the positive x-axis, and then the directed distance in the z direction. But the point I want to sort of emphasize here is that if you remember polar coordinates from Calculus 2, that r and that theta mean the same thing as they meant back in Calculus 2. And so cylindrical is just adding that z, but I mean the z is the same as it always is. So if we want to convert between rectangular coordinates and cylindrical coordinates, we have to come up with some formulas. But it's, again, since we've already done this in Calculus 2, this should be pretty easy. So for one thing, the z coordinate in rectangular is the same as the z coordinate in cylindrical. And again, if I'm given rectangular coordinates and I'm asked for the cylindrical coordinates, my r coordinate in cylindrical is going to be equal to what function of x, y, and z from rectangular?
Square root of x squared plus y squared.
Yep, that is going to be the square root of x squared plus y squared. just like from polar. And then if I want to get my theta, what is theta?
Arctangent of y.
Yeah. That's going to be like arctangent of y over x. But remember that the arctangent function is goofy and that you've got to be really careful because the arctangent function will only tell you about things in the first or fourth quadrant. And so sometimes we just write that tangent of theta is equal to y over x. Being very careful about that one. Okay. In the other direction, we can talk about cylindrical to rectangular conversion. And in this case, if I give you some point with r, theta, and z, and I ask you to give me x, y, and z, of course z is z, then how would I find x?
R cos theta.
Mm-hmm. Yep, that's going to be r cosine theta. And how would I find y?
R sine.
Perfect. R sine theta. Yeah. So that's the same as from polar coordinates back in calculus 2.
We're just adding the z, right?
Yeah, we're just adding the z because now we're talking about being able to describe a point in three-dimensional space. Exactly. Okay. So we'll come back to this and do some examples maybe at the end of class here. What might be a little bit new today is what we call spherical coordinates. Okay, if you were trying to locate some ship, like in the ocean, right? We don't have anything to like go off of, right? Like you can't just be like, oh, that's like 2 miles west of Midland, right? I mean, it's somewhere in the middle of like the Atlantic Ocean. What do we use? What kind of description do we use to describe the location of like a ship in the middle of the ocean?
Latitude.
Yeah. In our GPS coordinates, we talk about the latitude and the longitude, right? So we have our little globe. So here's like the North Pole. And we have these little great circles that pass through the North and South Pole. And these circles are what we call lines of longitude. And then we also have these little concentric circles, like the equator, and then all these rings that go up that are concentric around the North Pole and the South Pole. And we call those lines of latitude. And so if your ship in the middle of the ocean is right here, you would have to describe it using what is the longitude, which is like, you can think of that as the angle between sort of the axis of the Earth and somewhere in England? Or is it somewhere in the Pacific Ocean? Greenwich, yeah. And the ship, right? There's a certain angle. And then you also have to use an angle between the North Pole and the ship. There's like 2 angles that you use to describe the location of any point on Earth in these GPS coordinates. So, since the Earth is a sphere, we end up using 2 angles to describe anything on the surface of the sphere. In spherical coordinates, these coordinates are going to be what we call rho, theta, and phi. So this is not a lowercase p, this is the Greek letter rho. It's a lowercase rho. And rho describes the distance from the origin to the point. Theta describes the angle between the projection of the point in the xy plane and the positive x-axis. And phi describes the angle between the point and the North Pole. Well, I should say positive z-axis. Okay, so let me try to draw a picture. Here's my positive z-axis. Here's my y-axis, and here's my, oops. X-axis. So here's a point over here. And here is the projection of that point down into the xy plane. So rho is going to be the distance between the origin and where that point is in 3D space. Theta is going to be this angle here between the positive x-axis and the projection of that point down into the xy plane. And then lastly, phi is talking about the angle between the positive z-axis and the point in space. So whenever we talk about GPS coordinates, people are just giving you two numbers that describe theta and phi. Right? So theta is like the longitude of the location, and then phi is the latitude of the location. And we usually skip rho because rho is approximately the same on Earth, right? Like if you're talking about an object that's on the surface of the Earth, then rho is just going to be like the radius of the Earth. And I mean, Earth isn't a perfect sphere, but also we're not talking about identifying objects in different altitudes. We're just talking about something on the surface. And so in GPS coordinates, we just talk about theta and phi. But in our class, we're going to have to describe places in space with rho, theta, and phi. Does this make sense to everybody so far?
What motivates using cylindrical coordinates?
Huh?
What's the motivation behind the cylindrical coordinates?
We will definitely find out before the end of the semester. We're gonna, so, gosh.
So make our lives easier?
Yeah, yes and no.
Is it? Okay.
So like, you know, like with the single integral that we used so far in Calculus 1, Calculus 2. You're able to calculate areas of areas between the x-axis and the curves, or between curves. We're going to be able to use what we call double integrals to calculate volumes of objects in three-dimensional space. And then we'll also be able to use triple integrals to calculate like the mass of a three-dimensional object that has some density as a function of three-dimensional coordinates. So whenever we get into double and triple integrals later in the semester, sometimes those double and triple integrals are going to be in terms of the x, y, and z coordinates, and then sometimes we'll be talking about some kind of object in space that's easier to describe using spherical coordinates. Just as one example, spheres are easier to describe using spherical coordinates than rectangular coordinates, and so the math of doing those double and triple integrals is going to be easier if we use spherical coordinates. One really common one that has shown up a lot, it's like a favorite, is to like give students a question on an exam that talks about calculating the mass of like an ice cream cone, where like part of the shape is a cone but the top of it is like a half sphere, and so you use something like, you know, spherical coordinates because it's easier to talk about that three-dimensional shape. And then you'll calculate the triple integral where I give you the density as a function of rho, phi, and theta. And it makes your life easier in that the math problem would be easier than if you tried to do it with rectangular coordinates, but also harder because the problems are pretty hard. So, anyways, let's talk about how you would convert between rectangular and spherical real quick. If we want to do let's say a spherical to rectangular conversion, that means you're given rho, theta, and phi, and we want to find x, y, and z. Then I'm looking for formulas where I say, give me x, y, and z as a function of rho, theta, and phi. It actually might be easier if we start the other way. Let's talk about the other way first. So put a pin in that, and let's talk about rectangular to spherical. Okay. So this means you'd be given x, y, and z in this case, and we want to find the same point but in rho, theta, and phi. By the way, this symbol is a lowercase Greek phi, which is phi. Okay, so let's talk about these formulas first. If somebody told you the x, y, and z coordinates, how would you calculate rho? Remember, rho is the distance from the origin to the point in 3D space.
Is the magnitude of the vector 0 that point?
Yeah. It would be the magnitude of the vector whose tail is at the origin and tip is at the point. And so whenever we were calculating magnitudes, this was going to be the square root of x squared plus y squared plus z squared. Okay. How would I find theta if I were given x, y, and z? Yep.
Okay,
Yep.
and,
So, so remember, theta is the angle between the positive x-axis and the projection of the point onto the xy plane. So it's the same as it always is. It's the same as it always is. So tangent of theta is going to be y over x, where we are very careful because the arctangent function is not going to tell us the truth if our point lies in quadrants 2 or 3. So we got to be careful. How would I find phi? Let me draw a little picture for phi. So here is the z-axis. Here's my point. Here's my origin. So phi is this angle between the positive z-axis and that point.
tangent of phi is square root of x squared plus y squared over z.
Let me think.
Because the distance are the same on the xy plane and
Yeah, that would work. So there's a way to do it without having to use tangent, but I think that would work. I think you're right. That would definitely work.
you can use a phi, the row.
Yeah,
Yeah.
yeah, perfect. Okay, so that's what I'm thinking of. If I notice there's a little right triangle hidden in here, where, oh, oops, sorry, I drew that in the wrong spot. Here we go. There's a little right triangle hidden here, where this hypotenuse of the right triangle has length rho, the distance from the origin to the point. This angle is phi. Then that means this side length is going to be the z-coordinate of my point. So if I want to find phi, this is just going to be cosine phi is adjacent over hypotenuse. Okay, so if somebody gives you the x, y, and z coordinates and they ask you for the rho, theta, phi coordinates, rho is the square root of x squared plus y squared plus c squared. It's the distance from the origin to the point. Theta is the same as it always has been back to polar, right? Tangent of theta is just y over x, but we have to be careful. Phi, the easiest way of finding phi is to say, well, I already found rho, so cosine of phi is z over p, or we could say that phi is equal to arc cosine of z over rho, and arc cosine is a good function. you don't have to worry about it the way that we have to worry about the arc tangent function. So arc cosine is always going to work in that case. By the way, whenever we're talking about spherical coordinates, by convention, we like to have rho positive. So I should say rho needs to belong to the sets 0 to plus infinity, right? Rho needs to be a positive number. And it's like technically you could make rho negative and then just have it point to the opposite direction of whatever it is in space. But that's not our convention. Conventionally, we like to have rho be a positive number. Theta should ideally belong to the set from 0 to 2 pi. right? So 2 pi is a full rotation around the unit circle in the xy plane. And then phi ideally belongs to the set between 0 and pi. So if phi is 0, then you're pointing exactly along the positive z-axis. If phi is pi, that's pointing directly along the negative z-axis. But you shouldn't need any phi values that are larger than pi. If you were thinking about a phi value that was larger than pi, you should just change your theta. Does that make sense? Instead of going past a half rotation with your phi value, you should actually just rotate your theta value. And then always make phi between 0 and pi.
Is it open-ended pi to pi for theta?
Huh?
Is it open-ended to pi for theta or closed? Like it can't equal to pi for theta?
Well, if it was 2 pi, you could just call it 0,
Oh.
because you're just pointing along the positive
So
x-axis.
The parentheses.
Right. Yeah, that was intentional.
Oh.
Okay, so then the next question is, if we were given spherical coordinates and we wanted to convert to rectangular coordinates, how would we do it? Well, we can start from these that are a little bit easier to find. We can say, well, if I wanted to find z, z is just going to be rho cosine of phi. And we're given rho and we're given phi, so that's good. X and y are going to be a little bit trickier because rho isn't the same thing as r, so I can't just call it like rho cosine. Sorry, I'm blanking. I can't just call it rho cosine of theta like I used to be able to do with like cylindrical coordinates. Instead, we've got to kind of think about this a little bit. X would be the same thing as r cosine theta, but r is not the same thing as rho. R is what you would get if you projected this into the xy plane. So we have some rho here, and the length of the projection would be r. This angle is phi. So here's a little right triangle. This is z rho. This side would be the square root of rho squared minus z squared, I think. So this would be square root of rho squared minus z squared cosine theta. Now rho squared is just square root, it would be x squared plus y squared plus z squared. Yeah, so that might be the best we can do. Square root of rho squared minus z squared sine of theta. Okay. Yeah, so we can use z in these formulas because I can calculate z as a function of rho and phi. And so that's why I'm saying we could just calculate z first and then do that. Let me see if your book has a more clever way of doing it. Because that's probably how I would do it if I were trapped on a deserted island. But that doesn't mean it's the smartest way. Okay. So here's one more way to do it. And x you can find by writing rho sine of phi cosine theta, and y we can find as rho sine of phi sine theta. Yeah, that makes sense to me. Okay. So you can think of this as well. The reason this rho sine of phi shows up is because, again, of that right triangle that I just drew for you guys. I've run out of space. So here's the z-axis. Here is the xy plane. So here's our point. This angle is phi. This side length is rho. This side length is z. This side length, since it's the opposite since sine is the opposite over hypotenuse, this side length would be rho sine of phi. Okay. And so that means if you were going to try to convert from spherical to cylindrical coordinates, r is just rho sine of phi, if you're trying to go from spherical to cylindrical. Let's see if we can do an example. Okay, so let's convert this from rectangular to spherical. The point is -5, square root of 2. So I'm told this is in rectangular, and so that means these are the x, y, z coordinates. And I want to put it in spherical. So spherical tells me that rho is going to be the square root of x squared plus y squared plus z squared. So my rho is going to be root of what? Huh? Close. Yeah. 52. That's an easy mistake to make, though. Theta in spherical is going to be arctan of y over x. But again, we're going to be really careful about that sneaky arctan function. We're going to try to double check our answer after we do this. And so this is going to be saying that just tangent theta is equal to -5 divided by -5. Tangent theta is equal to 1. If I draw myself a little xy plane here, I think x is -5, y is -5. That's my point. Arctan is saying that I'm looking for this angle, and so that angle is going to be what? Hmm? Oh, yeah.
Yeah.
Good catch. Yeah, okay. So -5, -5, that should be down here. You're right. And since we want theta to be between 0 and 2 pi, then we're asking about what is this angle. Thank you. Here we go. What's this angle?
5 plus pi over.
Yeah, 5 pi over 4. Okay. So theta is 5 pi over 4. And then phi in spherical, I can find by asking what is arc cosine of z over rho. Because I'm saying, here's my z-axis, here's my xy plane. In the z direction, I've got this √2, and in the xy direction, I've got that distance would be √50, and I'm saying, okay, now what is phi right here? So phi is going to be arc cosine of z, which is √2, over rho, which is √52. And that's not an easy one. So this is where you would use your calculator. Does anybody know what this is?
1.37 radians or 78.7 degrees.
Did you say 1.37 radians? Okay.
What's on the double check?
Yeah. So it should be pretty, in my mind, this should be pretty close to pi halves. Because pi halves as an angle for phi, phi is the angle between the positive z-axis and your point. So if you get pi halves as phi, then you're talking about some point that's in the xy plane. This point is not in the xy plane. It's square root 2 above the xy plane, but this is a pretty small number compared to how far it is away from the origin, right? Root 2 is pretty small compared to root of 52. So I'm thinking about this point as being just barely above the xy plane, so my phi angle should be just a little bit less than pi halves. And so 1.37 sounds to me like it's a little bit less than pi halves, so that sounds completely reasonable. As sort of a sanity check on your answer. Okay. Ideally, I would work more examples for you guys. So what you should try to do sometime before next week, maybe over the weekend, is take a look at the homework problems I've assigned and try to work one of each type and just make sure you know how to do these conversions.
For the final answer, should we just put everything like on the, what's it called, on the spherical?
Yeah, so you could say your final answer here would be √52 for rho. And then theta was 5 pi over 4. And then phi is 1.37.
And for answer on phi, would we prefer to have it on radians or degrees?
I guess radians.
Radians?